In this video, we're going to look at the stability of benzene along with the definition of aromatic molecules. Aromatic molecules are typically defined as molecules that contain a benzene ring. In reality, aromatic is a much broader term. It doesn't have to specifically contain benzene, but you're looking for systems that are cyclic, conjugated, and that have a particular number of pi electrons. And we'll talk more detail about how to determine if something is actually aromatic or not in a later video. But here let's look specifically at benzene. So benzene is a six-membered ring, much like cyclohexane, but yet very different. It has alternating single and double bonds. Now you can draw double bonds in that location. You can draw the resonance structure where the double bonds are kind of in the opposite location. And in reality, benzene is kind of the average of those two. And one way it is very typically drawn is with a ring in the middle. So what you really have are bonds that are 1.5 bonds. So not single bonds, not double bonds, but it's somewhere right in the middle. And if you measure the bond lengths, you find that all bonds in the ring are the same length. So instead of having a short bond alternating with a longer bond, all of them are equal. It is also planar. All of your bond angles are 120 degrees. All 6 carbons are sp2 hybridized. And all have an unhybridized p orbital. And that unhybridized p orbital is what leads us to our aromaticity. So that allows the electrons to overlap around all of the carbons. So if we kind of try to look at this at an angle, all of those p orbitals you've got overlap around the top of the ring, overlap around the bottom of the ring, and those electrons are easily move from carbon to carbon. So this resonance aromaticity leads to benzene being much more stable than you would expect it to be. So if we look at some relative energies of hydrogenation, which is what we use to look at stability, if we make cyclohexane our reference point, so 0, if we then put in a double bond to make it cyclohexene, that energy is going to increase, the energy released whenever you do hydrogenation increases, meaning it's a little bit more stable, or a little bit less stable, excuse me. Add in a second double bond. Notice here the double bonds are conjugated, which we talked about in an earlier chapter. We are now at 230 kilojoules per mole. If we kept going with this pattern, you would expect benzene to be a little bit higher yet, but actually it falls down to where we are at 206 kilojoules per mole. So its stability is somewhere in between the cyclohexene and the diene version.